Welcome to the comparison of the medium voltage drive topologies. We have listed the main properties of a medium voltage drive system in the first column on the left of this table. Each drive topology has been evaluated against these key performance properties. These properties are critical in the overall efficiency, reliability and compatibility of your installation and its connected machinery. So, let's start. Start with the input harmonics generated by the investigated drive configuration. First in row is the Cycloconverter and the load commutated inverter, respectively CCV and LCI. They require transformers and filters to cope with significant harmonic distortion that they generate. The LCI often requires at least a 24 pulse in-feed. The pulse width modulation current source inverter PWM CSI needs at least an 18 pulse in-feed transformer, or it must be paired with an active front end to ensure a clean power supply. When equipped with an active front end, the 3-level neutral point clamped and the Modular Multilevel converter MMC are also able to operate with clean input power, generating minimal harmonic distortion. However, when used with a direct front end DFE, depending on the short-circuit ratio, these drives generally require an 18 pulse in-feed to comply with IEEE 519. The 2-level series Cascaded H-bridge provides for clean input power thanks to the cancellation of harmonics by phase displacement. We have about a multi-pulse input ranging from 18 to 54. The inherent power factor in the case of CCV and LCI must be corrected through a filter. For the PWM CSI, the active front end will be required to correct the poor load and speed dependent power factor. The drives starting from the 3-level up to multi-level relying on the direct front end have an excellent power factor over the whole speed range. The 2-level series Cascade H-bridge adds up the output of multiple low voltage power cells to obtain medium voltage levels. Each power cell is in fact a simplified version of a standard 2-level PWM low voltage drive with a direct front end. Therefore, this drive delivers the same excellent power factor as the ones we mentioned before with direct front end. Let's take a look at the output harmonics of our medium voltage drives. PWM CSI, the MMC multi-modular level, and the 2-level series Cascade H-bridge excel in sinusoidal output voltage, making them ideal for retrofitting or reusing the existing direct online motor. The drives with direct front-end in-feed can deliver a multi-level output voltage that is relatively clean of harmonic content. The Cycloconverter and the load commutated inverter deliver poor output waveforms, requiring special attention. The LCI will need a dedicated synchronous motor. Another critical aspect of the output of these drives is the voltage rise, DUDT. The 3-level NPC neutral point clamped inverter exhibits high DUDT values. Therefore, the connected motor must be rated for inverter duty to ensure reliable operation and installation integrity. A standard non-inverter rated motor requires a DUDT filter or a sine wave filter in this case. The common mode voltage is only a real problem for the PWM CSI, and this drive will always include therefore a common mode filter. Torque pulsations are significant in the Cycloconverter and in the load commutated inverter, even up to 8% in the case of a 12 pulse LCI. Depending on the drive machine, analysis might be recommended for the other topologies. It makes sense to validate the simulation results with real measurements. We refer to a 4-quadrant operation when the power flow from the machine towards the drive and the grid, is consistent, and regenerative operation is required. You can also operate indeed in the 4 quadrants with a drive using a chopper and a brake resistor, but when we refer to a 4-quadrant drive, we actually mean a regenerative drive that can send energy back to the grid. The Cycloconverter and the load commutated inverter and also the PWM CSI are what we call inherent 4-quadrant drives. Their configuration allows energy to be sent back to the grid. The other topologies, 3-level neutral point clamped multi-modular converter, require an active front end. The 2-level series Cascaded H-bridge is not readily available for 4-quadrant operation. Because of the lack of a common DC bus, breaking even via dissipation in a resistor becomes quite tricky and often economically unviable. Next in line, the motor type. Depending on the quite a lot of factors, the LCI can only drive, as already mentioned, a dedicated synchronous motor. And as mentioned before, also the 3-level neutral point clamp requires an inverter duty motor. While the PWM CSI and the MMC and also the 2-level series Cascade H-bridge can drive a standard motor ideal for retrofit applications, the 3-level neutral point clamp will require a sine wave filter or a DUDT filter for reliable operation. The performance of the drive relates in fact for the most part to the application requirements. The Cycloconverter performs quite well at low speeds with high dynamic overload capacity. The LCI load commutated inverter applications generally do not require high performance, and the relatively low performance of this drive is therefore not an issue. The dynamic response of voltage source inverters ranges from good to excellent, and components like reactors in the CSI do not limit them. PWM CSI offer superior performance, overcoming some drawbacks of natural commutated, load commutated and cycloconverter fed drives. The converter duty transformer can be integrated or installed independently from the drive. The cycloconverter requires 1 per phase, and all other topologies except for the PWM CSI with active front end require a multi-winding transformer realizing a minimum of a 12 pulse infeed. The 2-level series Cascaded H-bridge is always delivered with an integrated dedicated multi-winding dry transformer. The power range for each topology varies with the drive manufacturer. The load commutated current source inverter LCI is particularly suitable for power drives starting from 15 MW. The LCI can increase the drive's output voltage by adding thyristors in series, thereby increasing the available output power. The voltage source topology there requires a parallel unit configuration to achieve such high power levels, compromising reliability and increasing costs. While most drives require screened motor cables, the predominant concern will be motor cable length. This parameter must be carefully considered as additional filters might be necessary. And nearly finally, the redundancy in the power circuit. It helps to increase drive availability. This redundancy should allow the continuation of the process when a cell or power component fails. However, this is not possible for every kind of drive. The LCI, MMC and 2-level series Cascade H-bridge can offer these advantages. Restoring redundancy is paramount for the drive system's availability. Multidrive or common DC bus is another property. This operation is typical for sectional production lines and test stands, but it is only available in the 3-level neutral point clamped and the MMC topologies. Finally, cost comparison. It only makes sense for comparable applications, and the purchase costs represent only a small part of the total cost of ownership.